Welcome to this explainer. Today, we're throwing on our scientific detective hats. We're going to unpack a massive physical mystery and decode the hidden rules that actually govern how light travels through the universe. And the craziest part, we're going to measure the invisible using just a few everyday tools. Okay, let's dive right into this. You know when you're sitting at a restaurant, you look down at your glass of ice water, and that straw just looks completely broken right at the surface? It's a super common optical illusion, but what you're actually seeing is the universe showing off exactly how it handles the cosmic speed limit of light. But before we get bogged down in the math of measuring this, we really need to build some physical intuition. So to really picture why that straw looks snapped, think of a beam of light like a car cruising down a smooth, perfectly paved highway. Suddenly, the car veers off and hits a patch of rough gravel at an angle. The front tire hitting that gravel first, it's going to instantly lose speed. But the other tire is still flying fast on the pavement. So what happens? The car aggressively pulls or turns right into the gravel. Well, light behaves the exact same way. When it transitions from a fast medium, like air, into a slow medium, like water or a plastic trapezoid, it slows down and it bends. And that bending, that's what we call refraction. All right, here is our roadmap for today's investigation. First, we'll look at why light bends. Then we'll unlock Snell's law, jump into the plastic trapezoid experiment, and calculate the refractive index. After that, we'll explore total internal reflection, and finally, wrap things up with the critical angle test. Moving on to section 1, why does light bend? Let's figure out exactly how different materials actually influence the speed of light. Now, what's genuinely wild here is just how dramatic this slowdown can be. We use a total vacuum as our baseline. That's where light travels at its absolute maximum speed. But as soon as we start moving down into denser materials, the light really starts to struggle. In water, it's slowed down considerably, and by the time you get to a diamond, light is literally crawling at less than half its maximum speed. I guess even light wants to stick around a little longer when it's passing through a diamond. Those numbers we just looked at make up what we call the refractive index. It's represented by the letter N, and it's basically just a simple dimensionless ratio. You just take the speed of light in a perfect vacuum, which is c, and divide it by the speed of light actually traveling through whatever material you're testing, which is v. The main takeaway here is that the higher the refractive index, the slower the light travels, and therefore, the more dramatically that light ray is going to bend when it hits the material. So how do we calculate that exact bending angle? Well, that brings us to section 2, unlocking Snell's law. This is going to be our main mathematical tool for this whole investigation. And this beautifully illustrates Snell's law. When you look at the equation, you can see how it perfectly balances the conditions on both sides of a boundary. On the left side, you've got the refractive index of your starting material, say air, multiplied by the sine of the angle at which the light hits the boundary. Then, on the right side, you've got the exact same variables, but for your new material, like water or our plastic trapezoid. If the index n goes up on the right side, the angle theta absolutely has to go down to keep the whole equation perfectly balanced. All right, we've got the theory down, but now we need some actual physical proof. Let's head into the lab for section 3, the plastic trapezoid experiment. To really solve this mystery, we're going to run a classic refraction experiment to find the exact refractive index of one specific piece of plastic. And the setup is honestly incredibly simple. We just place a clear plastic trapezoid flat on a sheet of paper. Then we take a light box and shoot a single, crisp ray of light right into one side of the plastic. Finally, we trace the boundary of the plastic and make these tiny pencil dots right along the light's path so we can map out its entire journey. Following that map we just traced, you can see the light does exactly what we predicted. It starts out in the air, hits our plastic trapezoid at an angle. And because the plastic is a much denser medium, the light slows down and bends toward the imaginary normal line. That gives us our interior angle. Then it travels through the plastic and hits the boundary on the other side. But this time, it's going from that slow plastic back out into the fast air, so it actually speeds up and bends away from the normal line. By just connecting our pencil dots, we've perfectly captured these invisible angles right there on the paper. So the crucial point is we now have actual, real-world physical data. Let's crunch those numbers in section 4, calculating the refractive index. Our ultimate goal for this whole explainer is nailing down this one specific unknown variable, NPT. That stands for the index of refraction for our plastic trapezoid. Now, we already know the index of the air outside is right around 1.0, and we've just measured our angles with a protractor, so now We just have to solve for our one specific piece of plastic. Now, sure, we could just plug one set of angles into Snell's law and call it a day. But a good scientific detective knows that a single measurement is always prone to human error. To get a super accurate value for our one trapezoid, we have to repeat the experiment. We change the entry angle of our light beam to 10 degrees, then 20, all the way up to 80 degrees, carefully measuring that new bent angle inside the plastic every single time. And here's the magic. By plotting the sine of our incoming angles against the sine of our refracted angles on a graph, the slope of that resulting line gives us an incredibly precise, mathematically robust value for the refractive index of our plastic trapezoid. But wait, what if we messed up our graphing? We really need a secondary test to check our work. So, welcome to Section 5, Total Internal Reflection. This is the big plot twist of our explainer. Let's see how this builds on what we just found. Remember how light bends away from the normal line when it speeds up, like when it moves from plastic back out into the air? Well, picture those light rays radiating outward. As the incoming angle gets steeper and steeper, that exiting ray bends closer and closer to the actual boundary line of the plastic. Eventually, the angle gets so extreme that the light ray physically cannot bend any further without turning back inside. It literally can't escape into the air at all. It becomes completely trapped inside the plastic. And that exact tipping point? It has a name. It's called the critical angle. It is the highly specific angle of incidence where the refracted light ray bends a precisely 90 degrees, meaning it runs perfectly parallel along the surface of the plastic. And this is wild. If you push the light beam even a tiny fraction of a degree past this critical angle, the boundary of the plastic completely stops acting like a window. It instantly turns into a perfect mirror, reflecting 100% of the light back inside. Now, we can actually use this bizarre physical phenomenon as a tool. Let's get into Section 6, the critical angle test. So, we head back to our lab bench, we shine our light ray through the plastic trapezoid again, but this time we physically, slowly rotate the plastic piece right there on the paper. We keep our eyes on the refracted light ray exiting out the back. As we turn it, that exiting ray gets closer and closer to the edge. And the exact second that ray visually disappears entirely, we stop rotating. We trace the block, measure that internal angle with our trusty protractor, and boom, we have just found our critical angle. All right, now for the ultimate detective's reveal. We now have two completely separate methods to calculate the refractive index of our one specific plastic trapezoid. Method 1 used the slope of our Snell's law graph, right? And Method 2 uses a variation of Snell's law based on that disappearing critical angle we just found. We calculate the numerical value of the plastic using both methods. If the physical laws of the universe are holding true in our lab, these two numbers should be practically identical. But if they have a percentage difference greater than 15%, well, it just means our detective work was a little sloppy, and we need to grab our protractor and rerun those measurements for sure. And honestly, that is the true beauty of this explainer. We didn't need a multi-million-dollar particle accelerator to understand the fundamental physics of how light propagates through matter. By just grasping the principles we've covered, mapping a beam of light on a scrap of paper, and using a cheap plastic protractor, we essentially calculated the hidden speed limits of the universe. It really makes you wonder, if the profound secrets of light and matter can be completely unlocked on a standard desk with just a simple plastic trapezoid, what other incredible laws of nature are currently hiding in plain sight right in front of you? Keep questioning, keep measuring, and I'll see you in the next explainer.